Mr. Bowman here. In this video, we are looking at 2.7 calculus, and we're focusing on all the excellence questions from the 2015 NCA exam. So we're going to start off with question number 1. And in this question, we've been given a function, and we've been asked for what values of x will the function be decreasing. So decreasing or increasing relates to the gradient. So we're going to start off with by finding the gradient function. So if x will be equal to 8 plus 3x plus x squared minus 1/3 of x cubed. Noting I'm just changing that division to make it look like a fraction because I just prefer that, find it a bit easier. We then need to differentiate f dash x. The constant is ignored. And then that's going to be plus 3 plus 2x, and then 1/3 times 3 is 1, so that's going to be minus x squared. So, to the question, a function will be decreasing when the gradient, or f dash x, when that is less than 0, when that's any number. So we need to put that, or change our gradient function into an inequality. That is when 0, and then we've got 3 plus 2x minus x squared. So that's the inequality we need to solve. I don't like the negative x squared, so I'm just going to factorize out the -1 there. So -1 makes -3 minus 2 plus x squared. And then I can just make that look a bit easier. X squared minus 2x minus 3. And then I can factorize the bit inside the bracket. So that's -1 of x minus 3, x plus 1. Once we got to this stage, we've got a quadratic inequality. Just a reminder, you can't solve quadratic inequalities, but if you change that to an equation, you can find out the roots, and that will be a big help to doing this question. So that there is the equation version, and we know x1 is equal to 3, and x2 is equal to -1. This stage here, as I said, we can't solve an inequality, but if we draw this, that'll give us a big help. So we've got a negative parabola because of that negative x squared, and there are the x-intercepts. So we've got one intercept at -1, and then one at +3, and it looks like a negative parabola. So drawing it look like that. And we're trying to find out when is it decreasing, and that is when the numbers are negative. So if you have a look at the x-axis here, anything negative would be below the x-axis. So that would be these two portions here. And expressed as an inequality, this here would be anything less than -1, and that there would be anything greater than +3. So what that tells us is our original function will be decreasing when y is below -1 or when it is above -3. And we're just going to state that in a sentence form. So if x will be decreasing when y is less than -1 and when y is greater than +3. If you're able to step through all of that, you will be able to get your excellence mark. We are now looking at question number 2, and straight away I can see words like kinematics, we've got signal, and we had velocity up there. Yeah, so it's going to be a kinematics type question. We're going to start off with by jotting down the acceleration equation. So a in terms of t will be equal to 16 minus 2t. And that was given to us in the question. We know that the train passes the signal at 40, or at a speed of 40. So let's differentiate this, or integrate in our case. So if you've got the displacement, you can differentiate to get the velocity, and then we differentiate to get to the acceleration. This time around, we're going from acceleration to velocity, so we have to integrate. That there is going to be 16t minus 2 divided by power plus 1, and then we've got power plus 1 plus c. And when we clean that up, that becomes 16t minus t squared plus t. At the velocity of 40, so that's when we pass the signal, and that is when time is equal to 0, and when the velocity is 40 as well. So we're going to substitute both of those in. So we know that 40 will be equal to 16 times 0 minus 0 squared plus c. So that means c is equal to 40, and we've got our final complete velocity equation. The velocity is equal to 16t minus t squared plus 140 up there, but plus 40. We're now moving a bit more. We've been asked about how far. So far is a measure of distance, which is the displacement or the s value. So we need to go from the velocity to the displacement. We need to integrate again and go through the same process. Displacement in terms of t is going to be equal to 16 divided by power plus 1. Don't forget, the power there is 1, so we've added 1 to that. And then that is times by t power plus 1 minus 1 divided by power plus 1, t power plus 1, plus 40t, that one's a bit easier, plus c, and when we simplify all that, a bit messy, but that's going to get us to 8t squared minus 1/3 of t cubed, plus 40t plus c. Again, we've got the annoying c, but we do know, sneakily, we do know a bit more information. So when t is equal to 0, we have moved 0 meters from our original spot. And that makes sense. No time has passed, so we couldn't have moved because we've had no time to move. So we pop that into our equation. 0 is going to be equal to 8 of 0 squared minus 1/3 times 0 cubed plus 40 times 0 plus c. All of these are multiplied by 0, so they just kind of go away, which means c is equal to 0. So our final displacement formula, the displacement in terms of t is going to be equal to 8t squared minus 1/3 of t cubed plus 40t. The next part is really tricky. So that was fairly complicated, but pulling out the mass from the next part is really easy. So the first thing is we need to know how far. So we need to find a time value to put into our displacement formula. The only issue is we don't have a time value, but when it says stops, we've been secretly given a velocity idea. So when you are stationary, your velocity in terms of time is 0. So for every second you move 0, and that makes sense because you're completely stopped. So what we're going to do is we're going to go back to the velocity equation, and we're going to put in 0 as the velocity. So 0 is going to be equal to 16t minus t squared plus 40. Here we've got a quadratic. We could mess around by factorizing. We could mess around with the quadratic equation, but I'm going to put it straight into my calculator. So my a value is -1 because that's by the t squared. My b value is going to be 16 and my c value is going to be 40. I put that into my graphics calculator. T1 is going to be 18.2 seconds. And T2 is going to be equal to -2.2 seconds. And what we're going to do is we're going to ignore that negative number because a negative time isn't really realistic in this context because we're going forward, so we're not interested in that one. And that time value, that there is the t that we need for our displacement equation. So just above, I've gotten rid of the diagram. We're trying to find out the displacement at 18.2 seconds. So we're going to go 8 times 18.2 squared minus 1/3 times 18.2 cubed plus 40 times 18.2. We can simplify this, but don't waste time in the exam. Let's plug that into our calculator, and I'm getting 1,386 meters, and that there had a 0 dp rounding. So what that tells us is we have traveled 1,386 meters before we stopped completely. So very missing question. We were in and out, but we got there in the end. We are now looking at question number 3. Got that up there. We've got a skate park, and the amount is height meters in horizontal distance from the fixed point. So that the fixed point is on our initial diagram, or our top one over there. The mound can be modeled by this particular equation over here. The ramp So that's this mound here. They've now added a little ramp, which represents that line there, can be modeled by that particular equation, and it is a tangent to the mound as well. Use calculus to find the vertical distance below the top of the mound where the ramp will meet the mound. So we're going to start by drawing a bigger diagram. So there's our mound, and I'm just exaggerating the drawing just to make it a bit easier. And here we are. Here's our tangent. And I guess this question is really tricky because it was very difficult to understand what I was asking. But I was asking for the vertical distance below the top of the mound. So the top of the mound, let's say that's over here. You would have a horizontal line going that way. That would be the maximum height of the mound, where the ramp will meet the mound. And that's where the ramp will meet the mound. So we're trying to find this distance over here. So what's that gap? And that gap is going to be the difference between this part here. So let's call that H1. So that's the height of where the ramp meets the mound. And let's call this height 2, and that's just the maximum height of the mound. And we're trying to find this, which would be H2 minus H1. So we're going to start off by finding H1, and let's jot down the function that we're given of the mound up the top there. So Hx will be equal to negative 0.5x squared plus 3x minus 1.5. And we have been given a hidden bit of information at the point where the mound and the ramp touch each other. We have a gradient of 0.5 in the tangent function. So we know that h dash x will be equal to 0.5 in that part. So let's differentiate to find the function for h dash x. That is going to be negative x, or negative 2x, negative x 1/2 times 2 plus 3. So we need to figure out when that is equal to 0.5, which we got from above, negative x plus 3. So let's go minus 3 minus 3, so that there is negative 2.5 equals negative x. So x will be equal to 2.5. So that's the x value. That doesn't relate to height. Height would be, if you think of an x and a y-axis, that would relate to the y value. So we now need to substitute to find out what that y value would be. So this x is going to be substituted into the original height equation, and that'll tell us the height at that particular point. So the height when x is equal to 2.5 is going to be negative 0.5 times 2.5 squared plus 3 times 2.5 minus 1.5. In the exam, you could go ahead and do the maths just to get to your final answer, but I highly encourage you to use your calculator, and we're going to get a height 1 of 2.875 meters. We've got height 1, we now need to shift height 2. So let's work on height 2 over here. Height 2, we already have the gradient function from before, which is minus x plus 3, minus x plus 3. And this here would relate to the maximum. And at the maximum, we know that h dash x will be equal to 0. So what we're going to do is we're going to substitute that in. So h dash x will be equal to 0. We're going to substitute that in. So 0 will be equal to negative x plus 3. We're then going to go plus x plus x. So x will be equal to 3. We've now got the x value, just like we did before. We need to plug that back in to the height function, which is over here, and that'll tell us h2, or the height, or of the maximum of the mound. So h at 3 will be equal to 0, or negative 0.5 times 3 squared plus 3 times 3 minus 1.5, and plug that into your calculator. And I'm getting a height of 3 meters. So that is coincidental that we got 3 here and we've got 3 there. Our final step, h2 minus h1 is going to be equal to 3 minus 2.875. And when you get that, that is a 0.125 meter difference. So that means the vertical distance that they're talking about relates to that 0.125 meters. And that was the gap that we had up in here in our diagram. And now on to question number 4, and this is the same context of question 3 about the skate park. The height of a skate path, the horizontal distance is r meters from a particular point Q, and our skate park can be modeled by that. Straight away I'm seeing r cubed, which means it's a positive cubic, so it'll look a bit like that. But it does have a domain, so that probably tells us that a part of it will be topped off. So we might not have this bit, and we might not have that bit up the top. There is a height regulation of 3 meters above the ground, so that means at no point can it be above 3 meters above the ground. Fully describe this curve, including its turning points. So I'm going to start off with just by doing a bit of a sketch over here. So I'm assuming it kind of goes a bit like this. And if I was to describe this, I would need to know kind of how high it starts and kind of where that is. So that's the R value. I also need to know the same about the maximum. So I need to know the height and the R value for those. And again, with the minimum, I'll need the height and the R value. And finally, up the top there, I'll need the height and the R value. So I'm looking for all 4 points. If any of those points are above that 3 meter mark, that means it will not be in accordance with those regulations that we're looking at. So let's have a jump. So let's call that point number 1, point number 2, point number 3, and point number 4. So I'm going to start off by finding the minimums and the maximums that relates to points number 2 and 3. And we need to do that by differentiating our equation. So h is going to be equal to 1/3 of r cubed minus 2r squared plus 3r. H dash will be equal to r squared minus 4r plus 3. And I'm liking that because that's a quadratic, which means I'm expecting 2 answers, which makes sense because we've got 2 turning points, 1 min, 1 max. So those turning points, we know that h dash will be equal to 0. So 0 will be equal to r squared minus 4r plus 3. This time around, I can see that I'll be able to factorize that. So that's going to be r minus 3, r minus 1. So that means r1 will be equal to 1, and r2 will be equal to 3. So that tells us at this fixed point here, that one there is going to be 1 meter away, and this one here is going to be 3 meters away. So clearly that diagram is not to scale. Now that we know those, let's try to find the height of those, and we're going to find the heights by substituting both of them into our original height equation. So height in relation to r1 will be equal to 1/3 times 1 cubed minus 2 times 1 squared plus 3 times 1. Plug that into your calculator and you're going to get 4/3. And then we do the same for r2. We're going to get 1/3 times 3 minus 2 times 3 squared plus 3 times 3. And that there comes out to be 0. That means both of these points are below that 3 meter threshold. In particular, the minimum is on the ground level because it's at 0, and that maximum is 1 1/3 of a meter above the ground. We now need to look at the start and the end points just to see how high they are. We've been told from the domain it's going to start when r is equal to 0.125. So h when r is equal to 0.15. Plug that into your calculator and you're going to get a bit of a messy number, but 0.406125. And again, h when r is equal to 3.5. So just a reminder, I'm substituting these r's into that original equation. And that there gets us to 0.703125. And both of those are meters, just like the ones below, meters and meters. And that gives us information about the first and fourth points. We now know all about 1, 2, 3, and 4. So we're going to get to the describing part. So this skate path, or this skateboard path, will, and then just describe the points, it's going to start 0.15 meters away from, and don't forget we had that fixed point Q, from point Q at a height of 0.46. So 4.06125 meters above the ground. We then move on to the maximum, and we then move on to point number 2. So it increases to the maximum, which is 1 meter away from point Q, with a height of, and we found that 4/3 of a meter. So 4/3 of 1 meter. We then need to explain the decrease. It then decreases to the minimum, forgive me if I'm running out of room, which is 3 meters from point Q, with a height of 0 meters. And finally, our fourth point, we'll do it over here. Finally, it increases to a height of 0.703124 meters, which is 3.5 meters away from point Q. There we go. So each time we referenced the height and how far it is away from point Q, and I think that was a pretty comprehensive description. It would go well beyond what the answers we're looking for. The answers, if you were curious, we're just focusing on the minimums and the maximums. We are now looking at question number 5, and for the function y equals negative ax squared plus bx plus c, a, b, and c are positive numbers, and b is equal to 2a. We've been asked to sketch the gradient function of the graph we've been given, and noting the y dash intercept should be in terms of b. So what that means is we need to get rid of the a from our function. So let's jot down our original function. So y is going to be equal to negative ax squared plus bx plus c. Because we've been asked to sketch the gradient function, we're going to need to differentiate. So a dash is going to be equal to negative 2ax plus b. And on the side here, we're noting that b is equal to 2a. And our job is we wanted to get rid of a, so we need a by itself. So we're going to go divide by 2. So a will be equal to b over 2. And what I'm going to do is I'm going to substitute that in where the a is. That gets rid of the a, leaves only the b values. It's going to be negative a times b over 2 times x plus b. The times 2 and divide by 2 cancel each other out, leaving us negative bx plus b. And even though it looks a bit messy, that there is the equation that we need to draw. I've got a separate axis on the bottom right that we're going to draw on. And first thing to note, that negative b, so our gradient is equal to negative b over 1. So that means it decreases by b for every 1 unit that it goes across. And the b over here, that there is going to be the y-intercept. So let's just say this here is b, and if it goes down by b, it should go across 1 unit, which would set it over here, and that there would be 1. So let's just draw that a bit clearer. So it's going down b and then across 1, and then it would go down another b, across 1, down another b, across 1. This time around I made up that b was 3 squares. It actually could be any amount of squares. As long as you're consistent, you'll be all right. So that there is 1. Once I've done that, I'm now just going to connect the dots. Forgive the bad line. Hopefully you would have used a ruler to do that. And there you go. That's our sketch of the gradient function. And key thing is I've labeled my y-intercept in terms of b as we're told by the question. We are now looking at question number 6. And y is the value of x after 3 is subtracted and then the answer is doubled. So we need to form an equation. So y will be equal to x minus 3 and then it is doubled. And we have been told about a domain. That's only true for values between -1/2 and +3. We've been asked to find the minimum and maximum values when x squared and y are multiplied together. So let's start off by forming that expression. So our function, x is equal to x squared and y. And what I'm going to do is I'm going to substitute this y in over here, get rid of the y, put in the x. So that means x squared times 2, and then in brackets x minus 3. That there is going to be equal to 2x squared, x minus 3, which is equal to 2x cubed minus 6x squared. So that there is our function. Now turn our eyes to this idea of the minimum and the maximum. So it is a cubic, so we're expecting 2 turning points, probably 1 min, 1 max. And what we know is at those points, we know the gradient, or f dash x, is equal to 0. So we need to differentiate this. F dash x is going to be equal to 6x squared minus 12x. And we're then going to get rid of f dash x and put in the 0 gradient, which we know to be true there. So that's 6x squared minus 12x. We're now going to solve for x. So this is a quadratic. I'm going to look to factorize because I can see some 6's in common. 0 is equal to 6x, x minus 2. Our first answer for x is equal to 0, and our second answer for x is equal to positive 2. Now, these relate to the x values, but they don't give us the overall product. So what I'm going to do is I'm going to substitute both of these values back into the function to find out what the product would actually be. So just to the side here, so if f is equal to 0, we have 2 times 0 cubed minus 6 times 0 squared. That there is equal to 0. And if it is equal to 2, we've got 2 times 2 cubed minus 6 times 2 squared. 2 cubed is 8, times 2 is 16. 2 squared is 4, times 6 is 24. And there is going to be minus 8. Because this value is bigger than this value, we know that this here is going to be the maximum, and this here is going to be the minimum. So, geez, a nearly half an hour video, but that wraps up the excellence questions from the 2015 exam. Hopefully you found all the explanations useful. Excellence questions are really hard, requires lots of practice, so make sure you look at the other exams you have available to you. Thanks so much for watching, guys. Now let's keep practicing.